We opened our discussion of characteristic functions using Dynkin's multiplicative systems theorem in its complex form to show that the Fourier transform uniquely determines the measure that it came from, at least in principle. It turns out that, practically speaking, this is also true. We can functionally recover a measure from its Fourier transform, at least in one dimension. There are tools to do so in higher dimensions, but we will not discuss those presently. Here's our concrete theorem. If mu is a Borel probability measure on the real line, then for any a less than b in the real line, we can recover the measure of the interval from a up to b with the following integral. We take the Fourier transform of the measure mu, which is our input, and integrate it against this complex density on the compact interval from minus r up to r, renormalize, and then take the limit as r goes to infinity. That shows that we can recover the measure of any such interval. Except, unfortunately, it's not quite true. There's an additional term, 1/2 the measure of the two endpoints. So the endpoints pick up only 1/2 of the mass from this integral, not their full mass. So that looks like it mucks things up a bit. How do we recover the measure of an interval, because these are inextricably linked? Well, it turns out using a very similar formula, we can recover the mass of any one point, just by taking, essentially, the Fourier transform of mu hat with a minus sign, except we are integrating over a compact interval and then letting that compact interval grow, but also rescaling by its length in order to focus down on the point A. We're going to prove this general inversion formula right now. The proof of this one is very similar and will appear on a future homework for you to work out. Now, I want to point out something important before we proceed to the proof. It seems like this is just a Riemann-style improper integral, which we showed is just the same as recovering the Lebesgue integral, right? Well, there is a subtlety here. This function need not be L1. It goes to 0 at infinity if the measure has a density with respect to Lebesgue measure, but even in that case, that decaying density need not be in L1. And so there's no way that we could in general expect this formula to be the same thing as just the Lebesgue integral of the quantity inside here, since it wouldn't make sense for all measures, and yet it's supposed to recover this finite quantity on the right. In fact, by taking this limit, we are taking advantage of oscillations here and here that can cancel each other out, so that even though this function on its own is not L1, this integral does have a finite limit as the bound goes off to infinity. Now, one thing that is true and important to realize is that this oscillating density inside here at least is a bounded function of xi. And one easy way to see that is to note from the fundamental theorem of calculus that it is equal to the integral of the Fourier multiplier on the interval from a up to b, up to some sines and a phase. And therefore, the modulus is less than or equal to the integral from a up to b of dx, or b minus a. It's also clear that this function is continuous, at least away from xi equals 0, and using Taylor's theorem, it's also clear that it's continuous at 0. And so this integral at least makes perfect sense as a Riemann integral on any compact interval. The trick is to show that this limit converges to the measure over here, so we can recover its value on intervals, and therefore on all Borel sets in principle. In order to accomplish that, we need one fun calculus lemma, and that is that the integral of the sinc function is nice. So if r is any non-negative number, if we define s of r to be the integral over the symmetric integral from minus r up to r of the sinc function, then that function is continuous on the positive real line, including 0, and the function here is actually integrable. The limit as r goes to infinity of s of r is the finite number pi. And we get this from one simple trick. We write the reciprocal 1 over xi as the integral from 0 up to infinity of e to the minus xt dt. This is a trick that you may find useful in many other settings as you go forth. So as such, we can then write the integral in question, s of r, first of all using symmetry, since this, as a ratio of two odd functions, is an even function, as twice the integral from 0 up to r. Now we replace the offensive 1 over xc with this integral. And then we note that both of the functions involved here are bounded, continuous, and as you can easily check, for fixed xc, this function of two variables is integrable in t, and for each fixed t, this function of two variables is integrable in xc. Therefore, we can use Fubini's theorem to evaluate the integral in the other iterated order. Now, the inside integral with respect to xc is the kind of function that we can explicitly integrate by doing a double integration by parts, or to be honest with you, by asking Mathematica. And the result is this trigonometric function of t and r. Now we need to integrate that with respect to t, and since this Cauchy density 1 over 1 plus t squared is in L1, there's no issue with doing that, especially since the other functions of t here are bounded. Now the integral of 1 over 1 plus t squared is pi over 2, and so combining terms together, this double integral becomes pi minus this integral here. Now from this formula here, we easily see that s of r is continuous. In fact, it's c infinity, which we can prove by differentiating repeatedly under the integral using methods that we now know and love. We can also see that as r goes to infinity, this stays bounded, this decays exponentially fast to 0, so the integrand goes to 0, the whole thing remains uniformly bounded by, say, e to the minus t times 2 over this, which is a very integrable function, and therefore by the dominated convergence theorem, this second term goes to 0 as r goes to infinity, which yields the limit pi in the end, concluding the proof of this lemma. So with that in hand, we can now compute the Fourier inversion formula quite simply as follows. Let's define I of r to be this integral, which is the thing we're supposed to show, tends to the measure of the interval from a up to b plus half the measure of the endpoints as r goes to infinity. Well, first let's write out what the definition of mu hat is. It's this integral inside here. And now, as you might expect, we're going to swap the order of integration using Fubini's theorem. And I'll leave you to do the very simple justification of Fubini's theorem here applied to the real and imaginary parts of the function involved, the function of xc and x, which is nicely integrable and bounded and continuous in both variables, separately over the domains in question. Now let's recombine the e to the I xcx with the other exponentials here, which just gives us this translation of the variables inside. And now one quick thing to note about each of the two terms in this oscillator is that for any real constant alpha, like a minus x or b minus x, if we expand this in terms of its real and imaginary parts, note that the imaginary part is an odd function of xc, whereas the real part is an even function of xc. Now, since in the inside integral after Fubini, we're going to integrate over a symmetric interval, that means that this part of the integral will fall out, and we will simply get the same thing as integrating the real part of each of these two terms. So let's do that. The real part is this scaled sinc function, with alpha being one of these two terms, and so that gives us that I of r is given by this expression here. Now, the lemma we proved was exactly about the integral of the sinc function, but we have this extra constant inside dilating the xc. Well, that just means we need to do a change of variables. And if we change xc to eta, which is xc times x minus a, and do the usual substitution rule for Riemann integrals, we're going to get the function s of eta out when we integrate it, but there's going to be an extra factor out front involving x minus a, but that x minus a will be cancelled by the change of variables in the denominator, except it's not fully cancelled because it depends on the sign of x minus a, whether we'll get a plus or a minus sign out. And so when you do the calculus carefully, what you find is that, for example, that first term is equal to our function s, the antiderivative of the sinc function, evaluated at the scaled r times absolute value of x minus a times a plus or a minus 1, depending on the sign of x minus a, or a 0 if x happens to equal a. That is, we're using the signum function, which is equal to 1 on the positive real line, -1 on the negative real line, and 0 at 0. So putting that together with both of the terms, using this change of variables, we can rewrite I of r as 1 over 2 pi times the integral over the whole real line of this difference of signumed s functions. Now that's as close to an explicit expression for I of r as we're going to get, but remember that we're only interested in the limit as r goes to infinity. Let's look at what happens to the integrand as r goes to infinity. We proved in the previous lemma that s of r tends to pi, and since we're multiplying by something non-negative here, that's going to be true regardless. We're still going to get convergence to pi as r goes to infinity, unless x minus a equals 0, but then this signum out front, being 0, will take care of that. And so this goes to pi, and this goes to pi as r goes to infinity. The whole thing is bounded by the bound on s, which is pi, since it's actually an increasing function of r, and these functions here are less than or equal to 1 in absolute value, and so by the bounded convergence theorem, we get that the integral converges to the integral of signum x minus a times pi minus signum x minus b times pi against the measure mu. Now let's see what value this integrand actually has. It depends only on where you are in the interval relative to a and b. The first term, signum of x minus a, is equal to -1 below a, 0 at a, and 1 everywhere above a. The second term, signum of x minus b, is equal to -1 everywhere below b, 0 at b, and 1 above b. And so taking the difference of those, we see that below a, this difference is simply equal to 0. Also above b, on the interval in between, it's equal to 1 minus -1, which is 2. And at the 2 points, a and b, it's equal to 0 minus -1, which is 1, or 1 minus 0, which is 1. And that now nicely gives us our result. Taking into account this 1/2, that gives us the integral of 1 times the indicator of the open interval plus 1/2 times the indicator of the endpoints against mu, and that exactly equals mu of the open interval plus 1/2 mu of the endpoints, proving the inversion formula as claimed. One nice consequence of this general inversion formula is that it gives us an even nicer inversion formula for the probability density in the case where we happen to know that our measure has a probability density. And that, it turns out, is always true when the characteristic function actually is an L1 function. Here's our corollary. If mu is a Borel probability measure on the real line, and it happens to be true that the Fourier transform is an L1 function, then the original measure is actually absolutely continuous with respect to the Lebesgue measure, and we can recover its density rho by taking this integral here, which you should realize is up to a factor of 2 pi, exactly equal to the Fourier transform of the Fourier transform, evaluated at -x. I want to caution that this condition is very important and is not true of all probability measures. In fact, not even true of all probability measures of densities. Nevertheless, some version of this inversion formula actually holds in greater generality, in particular when the original function is in L2 rather than L1, and if you're interested in understanding that further, you should definitely go and take some courses in real and harmonic analysis. Let me also note that while we're only going to prove this in the one-dimensional case because we're going to use the Fourier inversion formula for measures that we just developed, the exact same statement holds true in general dimension, just with a factor of 1 over 2 pi to the d out front. So to prove this, we'll start with this putative density rho, defined by this Fourier transform of the Fourier transform. Now, by observing that fact that this rho is, up to a dilation and scaling, the Fourier transform of a function, which we're assuming is in L1, by the Riemann-Lebesgue lemma, this function decays to 0 at infinity. We'd like to see it's actually in L1, and that its integral reproduces the measure mu. So let's just integrate it over the interval from a up to b, which makes perfect sense because it's a continuous function, and so of course it's Riemann integrable on any such compact interval. We will now use the definition here, expanding inside, and you guessed it, we're going to do Fubini's theorem one more time, exchanging the order of integration. And it is easy to justify the conditions for Fubini's theorem here, since this function is assumed to be L1 of xi, and this function is bounded uniformly by 1 in xi. And for fixed xi, this function is certainly L1 on this interval. But now we can actually do that inside integral. In fact, we noted on the first slide of this lecture where that integral comes in. It is equal to the oscillator that comes into the inversion formula. And therefore, this integral just becomes this quantity here, which is more or less what appears in our Fourier inversion formula. We just have to note that in this case, it really is kosher to write this Lebesgue integral as the integral over a symmetric interval from minus r up to r, and then taking the limit as r goes to infinity, and that's because of our outbound assumption that mu hat is in L1, which means by the boundedness of this function that this whole thing is in L1. And since it's continuous, the Lebesgue integral and the improper Riemann integral are the same. Now we apply the Fourier inversion formula, and we get that this original integral amounts to this here, which is almost what we wanted to show, but of course, in order to show that this reproduces the measure, it must also reproduce the fact that the measure has no point masses anywhere. But we can see that just by taking a up to b in this formula. And that means that the integral from b up to b of rho, which of course is 0, is going to equal the measure of the interval from b up to b, open, which is the measure of the empty set, 0, plus 1/2 the measure of the point b. That means the measure of the point b is 0 for every b, and therefore this term is not actually there, and we conclude that rho really is the density of this measure as claimed. This form of the inversion formula, where we have an L1 characteristic function, is quite useful for identifying some characteristic functions. So, for example, just to belabor the point, we saw already that if x is a standard normal random variable, its characteristic function is e to the minus xi squared over 2, which is up to a constant the density of the original measure, the law of x. In particular, this function e to the minus xi squared over 2 is certainly an L1 function on the real line. And so, applying the theorem that we just proved, that means that the density of x, if we didn't know what it was already, is equal to 1 over 2 pi times the Fourier transform of the characteristic function of x, evaluated at minus the variable x. Now 5x is almost the Gaussian density, which we'll call gamma. It's just off by a factor of 1 over root 2 pi. And so that means that we can write this as, instead of 1 over 2 pi, root 2 pi over 2 pi, or again, 1 over root 2 pi, gamma hat at minus x. Now gamma is the density of x, and so its Fourier transform is written right here. And so this gives us 1 over root 2 pi e to the minus x squared over 2, but of course this density is symmetric, and so that again just gives us gamma, reproducing what we already knew. That's a very special case. In fact, it's the only time that up to scale the Fourier transform is given by the original density. In many other cases, we can use this Fourier inversion to identify the Fourier transforms of some functions that emerge as Fourier transforms of measures that we already knew. You're going to do such an example on your homework, but let's do another one right here. Consider the following probability density, the tent function, which, as you can see from the picture, really is a probability density. Now, we can explicitly calculate this Fourier transform. Rho hat of this density is given by this integral here. If we break that up over the interval from 0 up to 1 versus the interval from -1 up to 0 using the definition of the absolute value, we get this. But now if we make a change of variables, x goes to minus x over here, what we get is the same term twice except with a minus sign in this term. But that just means, since the minus sign up there makes this the complex conjugate of this, that we're adding the complex conjugate to itself, which just gives us twice the real part. And as we know, the integral of the real part of a function is the real part of the integral. Now, we could evaluate that by doing integration by parts, but instead, let's do the following. Let's break it up as the integral of the Fourier multiplier minus x times the Fourier multiplier. So we have this term out front there. And when we have the minus x in front, we'll again utilize our observation that multiplying by ix is the same thing as taking the derivative with respect to xi, and we can differentiate under the integral if we want here because of the niceness of the function involved in both variables. So we'll pull that out, and which means we'll only have to evaluate the integral of the Fourier multiplier and then take its derivative for the second term. And then I'll leave it to you to do that calculus and see that, in fact, the answer is this interesting function here, like the sinc function, except with a xi squared in the denominator. But that's possible here since the cosine function is even, and so subtracting it from 1 means that its Taylor expansion starts with a xi squared. Notice that this is a real valued function of the real variable xi, which we knew was going to happen in the first place because this is the Fourier transform of a symmetric measure. Great. Now, note the following. By the Fourier inversion formula that we just proved, if we now take this density, which we can easily see is actually an L1 function of xi, then this inverse Fourier integral of that L1 function just recovers the original tent function. And notice, by the way, that that means by taking x equal to 0 in here, and noting that that gives us value 1 here, that actually the integral of just that function is 1. It's also non-negative because cosine is less than or equal to 1. And so we conclude from this, changing the variable name, that the function 1 minus cosine x over x squared is a probability density, and that its Fourier transform is equal to 1 minus the absolute value of minus xi plus, which is the same thing as the original gadget. And so this tent function is the Fourier transform of some measure. That measure is the Fourier transform of the tent function. You'll explore some more examples like this on your own. That about concludes what I wanted to say about inverting the Fourier transform for one particular measure. But the more relevant question to us is, can this inversion be done robustly? How does it relate to convergence of characteristic functions versus weak convergence of measures? And that will be our final characteristic function topic in the next lecture.